Today we're looking at integration by parts. So if the function that we're looking to integrate is a product of two functions, then we can apply integration by parts to split the functions into their two derivatives, which can be very useful in terms where it's not immediately obvious what the antiderivative of something is. So go back to your base definition of product rule. If y is a product of u and v, then the product rule states that the derivative of that will be uv dash plus vu dash. So if we integrate both sides with respect to x, we can see that uv is equal to uv dash dx plus the integral of vu dash dx. So rearranging the formula gives us the formula for integration by parts. So what we're going to do is take this uv to the right hand side and take this vu dash to the left hand side. So I actually write it as integral of u dash v is equal to uv take the integral of uv dash. So when integrating a product, integration by parts may be suitable. So if we look at something like this, x sine of x, it's a lot easier to differentiate if that x wasn't there. So if we look at this uv dash up here, if our v term was x, our v dash term would be 1. And so it's much easier to just integrate 1 times sine x than it is to integrate x times sine x. So what we do is we define our variables. So in this case, u dash is equal to sine of x, which means u would be negative cosine of x. And then our v is x, which means our derivative of v is 1. So applying the formula of integration by parts, we start with integral of u dash v equals uv take integral of uv dash. And so, of course, substituting in, we get that the integral of x sine x dx is equal to uv, which is negative x cosine x, and then we get uv dash, which is the minus the integral of negative cosine x times 1. So we can see that's a whole lot easier to work with. So going to the next step, we've got negative, negative, so that's plus, and then the integral of cosine is sine of x, and then we also have our plus c term. So similarly in part B, we have x squared ex dx. Now, it would be so much easier to integrate this if that x squared wasn't there. So not only are we going to apply integration by parts once, but we're actually going to do it twice. So we start with our v term being x squared. We can then see that our v dash term is 2x, and our v double dash term is x. Okay, so by applying this twice, we're going to, v double dash is 2. So by applying this twice, we can see we're going to eliminate the x component. So our u dash, in this case, is going to be e to the x. So u is e to the x, and then we'll also have that the integral of that u is also e to the x. So let's apply our formula. We get the integral of x squared e to the x is equal to, so u times v is x squared e to the x. Then we're also going to have minus the integral of uv dash. So u is e to the x, v dash is 2x dx. But we still can't really integrate this because it's still a product. So what we're going to do is apply our formula to this again. So we get x squared e to the x minus, I draw a bracket because it's really easy to forget to distribute that negative to the new integral that we're going to make. Remember, it's uv take the integral of uv dash. So because I'm taking this entire integral, that second integral uv dash is going to end up being added. So I draw the bracket to remind myself that. So what is our uv in this case? Well, we've got u dash is e to the x, so we still get e to the x, and then we still have this v term, which is 2x, and we're going to be taking away the integral of e to the x times 2. Now, e to the x times 2 is much easier to integrate than what we started with. So what we get here is x squared e to the x take 2x e to the x, take 2e to the x plus c. And we can see if we were to differentiate that, this term would become 2x e to the x plus x squared e to the x. Then we'd also get 2e to the x plus 2x e to the x, and then we'd of course get minus 2e to the x. So, sorry, this term should be negative. So we can see cancellation there and there, cancellation there and there, and we do indeed get what we started with, x squared e to the x. So it's good to check that, but yes, indeed, the integration by parts is working for us. Okay, we then have determined the integral. Looking at example 15, we don't know what the integral of natural log of x is, but we do know that if you differentiate natural log of x, you're going to get 1 on x. So if we start with that as our v, natural log of x, our v dash then becomes 1 on x. And the benefit of that is we're going to be multiplying that by u later. So currently, if v is natural log of x, u has to be 1, because 1 times natural log of x is what's going on here. So if u dash equals 1, then u has to equal x. And we can see when we're looking at u v dash, x on x, well, that's just 1. So when we integrate that, that's just going to be x. So let's see this into practice. So u dash v equals uv, take integral of u v dash. So we get u times v is x natural log of x. We get integral of x on x dx. So x on x is just 1. So this becomes x natural log of x take x, because the integral of 1 is going to be x. We also have our plus c term. And what we could do if we felt so inclined is factorize this out. Take 1. And we could even take it a step further and make it x natural log of x on e. So that's, of course, using our log laws, knowing that 1 is natural log of e. So if we're subtracting natural log of e, then we're going to get x over e. Okay, our last example for today is determining the integral of e to the x sine of x. Now, for this one, what we want to recognize is that if we take v is equal to sine of x, and then we find the derivative of that, that's going to give us cosine of x, but then the second derivative of that will be the negative of what we started with. So if we apply the integration by parts twice, we're going to get the integral that we started with. And you'll see there's some interesting stuff that we can do when we have that. So if this is the case, we need our u dash, which is going to be e to the x. We need our u, which is still going to be e to the x. So let's apply this. So the integral of u dash v is equal to uv take integral of uv dash. So this becomes u times v is e to the x sine of x. We then get minus integral of e to the x, and then v dash is cosine of x dx. Well, we still can't do anything with that. What I'm going to note is that this is equal to e to the x sine of x dx. So if we could get this, like if this was sine of x, I could add it to the other side, and then I'd know what the integral is, because I just have to divide by 2. So let's try and apply it one more time and see if we can get it to look like the left-hand side. So on the right-hand side, I get e to the x sine of x take, so uv in this case is going to be, so if that's uv dash, it's going to be e to the x cosine of x, because of course this is u dash, it's becomes u, but it's still itself because the derivative of e to the x is always e to the x. And then we also subtract, don't forget our big bracket, the integral of e to the x negative sine of x. So times negative sine of x dx. And so this is where that negative distribution is very important, because this becomes a positive. If we tried to take it from the left-hand side, we'd get 0. So we have to distribute that second negative. This becomes e to the x sine of x, take e to the x cosine of x, and then minus because we've got three negative signs, e to the x sine of x dx. So my left-hand side is on both sides. So what I'm going to do is add this term to both sides. We get 2 lots of e to the x sine x dx is equal to e to the x, let's factorize this, sine of x take cosine of x. And so all we have to do now is divide by 2. So this becomes 1/2 e to the x sine x take cosine x. So that's our final integral there. So we can see something that even when we applied integration by parts, we didn't get any closer to the solution. But as soon as we applied it twice, we found our initial integral again. And so we can group our like terms, even though they're integrals, we can group them. And then we just divide by their coefficient. So really interesting stuff there. That's all for this video. Thank you very much for watching.